7.2 now, we are talking about rational exponents. So this is going to be our major review and revisiting of exponent rules, all the ones that we've been using this semester, as well as some new ones that you may or may not remember. So we have 5 things to talk about, much like the last section. I know that video went a little long, but this one shouldn't be. A lot of these will be review. So we need to understand a to the 1 over n. We need to understand a to the m over n. And we need to understand a to the negative m over n. We're going to revisit those rules of exponents. And then finally, we're going to be looking at rational exponents and radicals and how they connect. Actually, we'll be looking at that the entire time, but that's the big overarching theme in this section. So let's start with the definition of a to the 1 over n. So if n is a positive integer greater than 1, and the nth root of a is a real number, then a to the 1 over n is equal to the nth root of a. So our rational exponents, when we have fractional exponents, we are really implying that there is an nth radical that we need to find. Now we only have that if you can take the radical. So for instance, in the last section we talked about even indexed radicals, where n is 2 or 4 or 8 or something like that. A can't be negative. So if a is negative, you would never take the 1 over the 16th power, because that wouldn't work. So let's look at a couple examples here. So use radical notation to rewrite each expression, then simplify if possible. So 4 to the 1/2 is 4 to the, or is the square root of 4, which we know, since there's no negative in front, this is just 2, the principal. 64 to the 1/3 is the cube root of 64, which we know is 4. The x to the 1/4 is the 4th root of x. Now this cannot be simplified because we don't know what x is. Negative 9 to the 1/2, remember, without parentheses, this negative sits out front and is the negative square root of 9, which means we do not want the principal anymore. We want the negative root, which is negative 3. 81x to the 8th, all raised to the 1/4 power, using our traditional switch to 4th root of 81x to the 8th. The 4th power, or the 4th root of 81 is 3. And as we talked about, variable powers are perfect powers of n if they're divisible by n. So 8 divided by 4 is x squared. And I'm going to stick 6 underneath right here. 5y to the 1/3 is just 5 times the cube root of y. And we can't simplify cube root of y because we don't know what it is. Some practice problems here look very, very similar. Just getting used to making sure that we are applying our exponents properly when there are parentheses, when there are not parentheses, when negatives show up, and etc. So let's talk about the definition of a to the m over n. So I didn't delete this one because it looks nicer this way, but if m and n are positive integers greater than 1, with m over n in simplest form, then a to the m over n is the nth root of a to the m, or it's the nth root of a all raised to the m. So as long as nth root of a is a real number. The way that we choose this is whatever's easiest to calculate. So if it's easier to take the nth root first, then you use this version. If it's easier to take the mth power first, then we use this version. So let's take a look at that in some examples here. So 4 to the 3/2 power. Since The 1 over 2 tells us this is a square root of 4 cubed, or it's the square root of 4 cubed. I want this one, or to use this one, because I know what the square root of 4 is. It's 2 cubed. And so this is 8. Now if you were to cube out 4 to 64, that one's not too bad. We know that 64 square root of 64 is 8. On average, if you can take the nth root first, I would recommend it, but not necessary. Here we have negative 16 to the 3/4. So this is, the negative is not attached to the exponent, so this is negative cube root of 16 to the 4th, or negative cube root of 16 raised to the 4th. And 16 is not a perfect, oh, I did it backwards, 4th root cubed, 4th root cubed. So 16 is a perfect power of 4. So I would again want to do this. Not because that 16 cubed is not going to be a perfect power of 4, because it most likely is, since 16 is a perfect power of 4, but because it's easier to do the 4th root of 16 than it is to cube 16 and then take the 4th root. So this is negative, the 4th root of 16 is 2 cubed, which is 8. For number 3, since the negative is in the parentheses, this is the cube root of negative 27 quantity squared, or it's the cube root of negative 27 that then is squared. And again, I could square negative 27. I could use the calculator and do that. But I already know that negative 27 is a perfect cube, so why not just do that? And the cube root of negative 27 is negative 3. And this is quantity squared, which is then 9. And if you were to multiply out negative 27 times negative 27, you would get what 9 cubed equals. So you can go either direction, but you want to think about what's easier for you to calculate. So number 4 here, the negative stays on the outside. This is the square root of 1/9 to the 3rd, or the negative square root of 1/9 to the 3rd. Again, you could cube it on the inside. I'm sure that 9 cubed is a perfect square, since 9 is a perfect square. But I can do the square root of 1/9 in my head without having to go to the calculator. So this would be negative 1/3 quantity squared, which then gives me negative 1/9. So it's all about what's easier to calculate. And then finally, number 5 here, 4x minus 1 quantity to the 3/5. This is the 5th root of 4x minus 1 cubed, or the 5th root of 4x minus 1 quantity cubed. I can't really simplify either of these. There's no sense in expanding this out as a binomial cubed, because if it's a power of 3, it's not a power of 5. Which means even if we expanded it out, we wouldn't be able to simplify it. So we leave it in one of these two versions. Okay, well, let's turn the page here. There are a couple practice ones. Again, they look very similar. Think about what's easier to do, the root or the power first when you're working those out. But we're going to talk about the definition of a to the negative m over n. So as long as a to the m over n is a non-zero real number, then negative a to the negative m over n is equal to 1 over a to the m over n. Since our negatives just push things from the bottom to the top or from the top to the bottom, which of course is then 1 over the nth root of a to the m, or 1 over the nth root of a to the m. And again, you pick the one that's easiest to calculate. So we've got two quick examples here, because these are just like the last ones, only with negatives. So 16 to the negative 3/4. This is 1 over 16 to the 3/4, which is 1 over the fourth root of 16 cubed. We know that the fourth root of 16 is 2, so this is 1 over 2 cubed, which is 1 over 8. Same thing with number 2 here. Negative 27 to the negative 3/4. This is 1 over negative 27 to the 3/4, which is then equal to 1 over the fourth root of negative 27 cubed. Now, this is where we go back to the definition. A to the m over n has to be a non-zero real number. Well, are we allowed, excuse me, are we allowed to take the fourth root of a negative? The answer here is no. So this is, I ran out of space, so I'll write it here, undefined. Because of that negative there. And I purposely went through the steps because maybe you don't see it as a fraction, as a power, fractional power here, but it's very apparent once you switch it to your radical. Oh, excuse me. It appears I got the hiccups. Okay, so let's talk about the rules of exponents. So some of these should be reviewed. They're ones that we've been using. Some of these are going to be maybe ones that you didn't remember quite so much. Excuse me. So we have the product rule for exponents. This says that a to the m times a to the n. We add our exponents, a to the m plus n. We've been using that almost since day one. The power rules for exponents, there are 3 of them. A to the m, all to the n. We multiply exponents as a to the mn. A over c to the n. This is a to the n over c to the n, so it gets distributed to each. And then finally, a times b quantity to the n. It gets distributed a to the n, b to the n. So we've seen these, we've been using these. The quotient rule for exponents, should have given more space. This is a to the m over a to the n. This is a to the m minus n, as long as a does not equal 0. The 0 exponent is a to the 0 equals 1, as long as a is non-zero. And the negative exponent rule that we've been looking at this time, a to the negative n equals 1 over a to the n, again, provided that a is not 0. Now notice that m and n are rational numbers in this definition. So this includes, all of these are valid for these types of rules where we're talking about m over n because they're rational numbers. And so this is a nice list of our exponent rules for you to use. And we're just going to go through a bunch of examples now, simplifying using these rules in combination with fractions, some non-fractions, and a bit of both. So let's start with x to the 1/2 times x to the 1/3. This is going to be a product rule for exponents. So this is x to the 1/2 plus 1/3. And so really what this is a problem where we're adding 1/2 plus 1/3. So this is going to be x to the 3/6 plus x to the 2/6 to get a common denominator. And this is going to be x to the 5/6 is our final answer. For number 2, 7 to the 1/3 over 7 to the 4/3. This is a quotient rule. So we're going to do 1/3 minus 4/3. So this is 7 to the 1/3 minus 4/3. I'm going to bring that down here. 1/3 minus 4/3 is negative 3/3, which is just negative 1. So this is just 1 over 7. Y to the negative 4/7 times y to the 6/7 says that we add. So this is y to the negative 4/7 plus 6/7, which gets us y to the 2/7. Five to the 3/8 raised to the 4. this is our first power rule for exponents, so we multiply 5 to the 3/8 times 4, which is 5 to the 3/2, which is then 125, the square root of 125, which is then 5 rad 5, because 5 cubed is 25 times 5, and that would be our final answer. Here we need to do a little bit of simplification. This 5 needs to be distributed just like it is in this power rule for exponents, distributed to both terms, and then we need to multiply 2/5 by 5, and the 2 to the first needs to be multiplied, so this is 2 to the 5th, x to the 2/5 times 5 over x squared. So this is 2 to the 5th times x to the 2nd over x to the 2nd, which is then just 2 to the 5th, which is 32. So all of this was using exponent rules. We have the exponents, but the bigger purpose of this entire section is so that when we look at problems like this now, we can use these exponent rules, convert our radicals to exponents, and then simplify. So I'm going to work the problems down here, and then you'll have some practice problems in Canvas for you to try out that are similar. So the 8th root of x to the 4th is x to the 4th to the 1/8 power. Because we know that the radical, the index of the radical, means it's 1 over that number. And now we can use our power rule for exponents. And this is x to the 4th over 8. Simplifying, this is x to the 1/2. So this is the square root of x. This is how we can simplify that. Number 2, the 6th root of 25. Well, this is 25 to the 1/6. And then you may be looking at this and goes, what do we do? Think about 25 is 5 squared. And that would be raised to the 1/6 because the whole 25 is being raised. This is really 5 to the 2 over 6 using our power rule for exponents and multiplying. And so this is really 5 to the 1/3 or the cube root of 5. So now we've simplified without having to approximate. Number 3, the 6th root of r squared s to the 4th is r squared s to the 4th all raised to the 1/6. We distribute our 1/6 and multiply, so this is r to the 2 over 6 times s to the 4 over 6, which is r to the 1/3 times s to the 2/3. And now what we actually do here is we refactor out that 1/3 because we know that with our power rule of exponents, it can go in both directions. So instead of distributing, we factored it out of the exponents. And now we have the cube root of rs squared as our answer. And number 4, we have the square root of x times the 4th root of x. And this is x to the 1/2 times x to the 1/4, which means that we're going to add exponents, x to the 1/2 plus 1/4. And this is x to the 2/4 plus 1/4, getting common denominator. So this is x to the 3/4, which is then the 4th root of x cubed. Or the 4th root of x, quantity cubed, depending on what version you want. So we were able to take a 2-radical expression and write it as one single radical. Number 5, we have the square root of x, I don't know why I wrote equals, over the cube root of x, or x to the 1/2 over x to the 1/3. Using our quotient rule, this is x to the 1/2 minus 1/3. And so that's going to be x to the 3/6 minus 2/6, getting common denominator in those fractions, or x to the 1/6, or the 6th root of x. And then finally, number 6 here, the cube root of 2, or the cube root of 3 times the square root of 2. This is 3 to the 1/3 times 2 to the 1/2. And so what we do is we get common denominators, 3 to the 2/6 times 2 to the 3/6. And then we can factor out the 1/6 much like we did up here. So we have 3 squared times 2 cubed to the 1/6. And so this is 9 times 8 to the 1/6, or the 6th root of 72. So now we've taken this, what looks like a gross 2 radical thing that we can do nothing with, and wrote it as 1 radical. Okay. And like I said, there's some practice problems in Canvas for you to work out in this section, doing very, very similar stuff to this, writing everything as 1 radical. Oftentimes your instructions for the problems will say, simplify the following using exponent rules, write your answer as a single radical. Notice all of our answers were 1 single radical in all of these problems.